All right, today's date is 1/7, and the title of the section is going to be called Determining Population Size. Okay, so determining population size. So all along here we've been talking about populations and how big they are, how they change, do they get bigger, do they get smaller, and how does that go about working. And we're going to talk about how biologists, ecologists, people work in trying to determine the size of populations. The first way is called direct observations. Alright, so direct observations are going to be where I basically go out and I am going to count all the members of a habitat. Right, so if I wanted to know how many cardinals were out in our woods, I would simply go out there, I would count each one, and I would say that there are this many cardinals in our woods. Okay? And that's fine when we're working with smaller numbers, but that doesn't always happen. Okay, if I was looking and I came to a mound of ants and there were thousands and thousands of them moving all around on top of each other and over each other and in and out of the hole of the mound, and so it'd be very difficult to count up how many there were. All right. So in those situations, or if you're not able to see the animal or the organism, you would use what is called indirect observation. And when we're working with indirect observation, one of the methods is called sampling. Okay, sampling. And sampling is the idea of taking an estimated number based on a reasonable assumption. So it's taking a estimation based on a reasonable assumption. Yep.
Wouldn't it be taking an estimation?
Sure. Alright. Now, let's take, for example, let's say that we have birch trees. We'll use 8 birch trees. And let's say that we have 10 meters squared of our area. And we remember from math that area is length times width. And so let's say that we have 10 meters by 10 meters. Okay? And let's say that there are 8 birch trees. 1, 2, 3, 4, 5, 6, 7, 8. So there are the 8 birch trees that are sitting there.
What's the last word after that new sentence?
This?
Yeah.
Assumptions. And so what we do for a sample is we took just a small area. Okay, we just took this 10 by 10 area and we counted up the number. Now what we can do is we can try to figure out what it would be for a much larger area. Let's say that I wanted to know what it was for 100 meters squared. Does anybody have a way of trying to figure out how many birch trees there would be? If we know that there's 8 birch trees in 10 meters squared. Alex?
Well, you can, since 100 is 10 times 10, you can take 8 times 10, and that's how it would be.
Yeah, so how many would there be?
80.
Yeah, so there would be 80 birch trees, if we were assuming and we counted that there was going to be 8 on that 10 meters, we'd say that if it stays consistent, we would expect there to be 80 birch trees on 100 meters squared. Okay, so if we had 100 meters squared, so a bigger area, we'd expect that there'd be all the way up to 100 or 80 on that 100. Okay, what happens if I said that there is 1,000 meters squared area? How many birch trees would be found there? Yep.
800.
800. Okay, so everybody sees how we are able to take and figure out based on just a small sampling. Now, could we be more specific? Could we figure out what it would be for 2,000 meters? Yeah, we could sit there and keep going and figure that part of it out. Okay, so that's called a sampling. Sampling. The one that you just finished up, or some of you are still working on, is called mark and recapture method. Okay, this one we just got done in the lab with. And mark and recapture is basically, if we take our example that we used for the lab, where we had a pond, and you go to the pond and you are going to collect as many of the snapping turtles as you possibly can. And each time that you take one out, you are going to count it. So you have something there that you're going to use to count, whether it's paper and pencil or you have a computer. And you're going to tally up how many that you count, how many that you collect, and you're going to mark it. Or tag it, however you want to. And so you're going to mark it, count it, and put it back. Okay, so it goes back into the well. And so that first time that you are there, you're going to do this until you try to get as many snapping turtles as you possibly can. Okay, so you might spend the whole day there just trying to collect as many of them as you possibly can. And if you get one that has a tag on it, you put it right back. You try to get another one that doesn't have a tag until you have as many of them as you possibly can. And then what you do is you come back later, okay, maybe a week later, maybe a month later, maybe a couple months later, and you're going to again collect. And this time you're going to use a specific formula to try to figure out what the estimated total population is. Okay, you're going to use the formula of number marked times the total number captured divided by the number captured with marks. Alright, so let's say, for example, the first time that you came to the pond and you had 50 turtles that you counted. Bless you. And you also marked 50 of them. Okay, so that first day when you were sitting in your boat or wherever that you were going to be collecting these turtles, and you counted up 50 of them. And on all 50 of those, you marked each one of them. So there were 50 marked. You come back, let's say, a week later, and you start to try to collect as many as you can again. This time, you are able to collect 30 of them. And this time, 15 of them are marked. Can somebody help me set up the equation so we can try to figure out what the population is of this pond using our formula? Yep.
So you would do the 50 times 30 divided by 15.
All right, excellent. Okay, we had 50 because we said that it starts off with the number marked, okay, and we said that we originally started with 50 marked, times by the total number captured, and so we said that this time we captured 30 of them, divided by the number captured with marks, which is 15. Okay, and so when we do that, we have 50 times 30, which gives us 1,500, divided by 15, ends up being 100, would be the estimated total population. Okay, so those are two ways that we could try to figure out what the population is based on kind of looking at the habitat, kind of looking at the different parts of the habitat and how they fit together. Now, that doesn't include what happens when there are births and deaths. Okay, so we have to introduce the term birth rate. Birth rate is going to be the number of births in a population in a certain amount of time. Okay, so basically how many babies that the organisms are going to have in that habitat over a certain period of time. The exact opposite then would be death rate, which is going to be the number of deaths in a population in a certain amount of time. Okay, so I'll give you a chance to get caught up there. So the two of them kind of work opposite of each other, increasing populations or decreasing populations. Okay, so you have death rate, population goes down, birth rate goes up, we see the population go up.
They work opposite of each other, but they kind of work together to make like a unity.
Yeah, to make the balance, And in fact, what we have is birth rate, so if I can abbreviate, BR. In math, what does that symbol mean? Greater than. Death rate, so if the birth rate is greater than the death rate, the population, I'm going to abbreviate population, will go up, and the exact opposite is true. So if the death rate is greater than the birth rate, the population goes down. So we can either see a population increase or decrease based on birth rates and death rates. Now, it's not always just babies being born or things passing on that causes a population to decrease or increase. What can also happen is we can see an organism leave a habitat or come into the habitat. So we have a term that's called immigration, which is when an organism leaves a population. Okay, maybe there's more food or more water somewhere else, and so it leaves its habitat to go somewhere else. Immigration is when an organism is going to enter a population. So maybe there's more food or water in this habitat that allows for the organism to move here. And these can obviously have an effect on population sizes. Okay, if we see a tremendous amount of immigration, population goes down. If we see immigration coming into the area where there's lots of organism entering, the population is going to go up. And because there is this constant changing of populations getting bigger, populations getting smaller, scientists use a formula for the term population density. Okay, population density, we learned density earlier this year. Density is the amount of mass per the amount of volume. Volume being the amount of space that something occupies. So basically what we're trying to do with population density is we're trying to figure out the number of individuals in an area of a specific size. So the number.
What's immigration again?
Immigration is entering a population.
I meant
Immigration,
Yeah.
leaving a population. So it's the number of individuals in an area of a specific size. Okay, so that's what population density is. And the formula for it is population density equals number of individuals divided by unit area. Okay, and I'll give you an example in a second after you get a chance to get caught up there. Okay, so one of the ways that we can figure out how many individuals are in the area is based on population density. Okay, we take the number of individuals, we divide it by the unit area. So if we take, we'll take butterflies, we'll take monarchs. Let's say that we have 20 monarchs. And we'll say that we have a 10 meter squared area. So imagine that this is 10 meters by 10 meters. And so we have 20 butterflies. Those are butterflies. Beautiful, beautiful butterflies. So let's, for the sake of this, imagine that there's 20 that are in there. I have no idea how many I have anymore. But there's 20 in there for our make-believe land right now. So how can I figure out what the population density is using my formula? What do I have to do to what here in order to figure out what the population density is for this? Yep.
I think 20 times
divided by what?
Unit area, which is like 11.
10. Yep, so we have 20 monarchs. These are the number of individuals. Okay, so the number of individuals, which we said goes on top. Okay, so the number of individuals, which is 20. And then the unit area, which is going to be 10 meters squared. Okay, so what is the amount of monarchs per the amount of a meter? Okay, Spencer?
2 per meter.
Okay, so what it ends up being is that there are 2 monarchs per, remember that slash sign means per, meter. Okay, so meter squared. So what ends up happening is that for every, imagine this is a meter by another meter, so this is your little square. Okay, that means that there's going to be 2 little happy butterflies that are going to be in that area. Okay, and so that's our population density. How dense or how much there is of an organism in a specific area. Yes?
What population density?
Population density is the number of individuals in an area at a specific time. Now, there's 2 terms and then we're done. Things that cause populations to, well, one thing that's going to cause a population to decrease, and then we'll talk about what the other one is in a second. This is called a limiting factor. Okay, a limiting factor is going to be an environmental factor that causes a population to decrease. Okay, some examples of things that could cause a population to decrease due to a limiting factor could be something like weather. If it gets too cold outside or too warm out for an organism to be able to survive, we might see that a population could decline because of this. Or if there's a lack of water, okay, or if there is a lack of food. Okay, those are things that could cause a population to decrease. And those decreasing factors are called limiting factors. Okay, and the last note, and we're done, is called carrying capacity. And we talked a little bit about this one when we did how many bears can live in the forest activity. And the idea of the carrying capacity, it is the largest number of organisms that a habitat can support. And I gave you the example of, imagine that, let's say there's 130 sixth graders. This is going to be our carrying capacity line. Okay, imagine that I'm cooking 130 hamburgers and you are so hungry, you haven't eaten, even if you don't like hamburgers, you know you have to eat. And so what happens is that every single sixth grader would get a hamburger. And everybody would be happy because everybody had the opportunity to have their needs met. They all received food. But if I told you that I'm going to step in and I'm going to have one of the hamburgers, this line is now going to go above our carrying capacity, which means that one of the organisms is going to either A, not survive, B, going to attack or compete with a lesser organism to try to take theirs. And so what's going to happen though, either way, is that this organism is going to be faced with a challenge. Is it A, going to die, B, emigrate to a different population, or it's going to compete with, C, compete with other organisms in there. And so what happens is that this line stays pretty consistent, this carrying capacity line. But what we see is that sometimes the population goes above that level, and what we'll see is that there will be a decline either through immigration or death or competition, and then it will come back down to the level. Sometimes due to limiting factors, organisms, there will be a huge decline in population, but then because of birth rate, it will start to come back up. And so what we see is this kind of, sometimes it goes above, sometimes it goes below the carrying capacity, but either way, it tends to stay right around that amount, because there has to be enough food, there has to be enough water, there has to be enough shelter, and there has to have all of these things for the habitat to be able to survive. Okay? And that completes our notes.